Americanized Hafen. Actual pronunciation is probably closer to Hafen. So I don't actually really know. I'm American thoroughly, so yeah. All right, can you hear me? So today I'll be telling you a little bit about using hydrodynamical simulations to study circumgalactic gas flows. Before that, I am Zach Hafen. I am a graduate student at Northwestern University /Sierra, where I am being advised by Clandre Faucher-Giguère. And the work I'm telling you about today wouldn't have been possible without the help of a series of fantastic collaborators whose names are shown here. So, as I mentioned, I'll be talking about the circumgalactic medium, and in particular, gas flows in the circumgalactic medium. And why do these gas flows matter to you? Well, for one, CGM outflows expelled from galaxies by galactic feedback can tell us about that feedback, and also about the resultant suppression of star formation. On the other side of things, EGM inflows are thought to be necessary to provide continued material for star formation inside galaxies. Now, one of the best ways to look at outflows and inflows is through quasar absorption line spectroscopy. And the problem is that quasar absorption systems have one-dimensional kinematics, and so therefore it's oftentimes very difficult to distinguish inflows from outflows. However, in recent years, it's been thought that perhaps metallicity would help us distinguish the two. And in fact, in 2013, Leonard et al. Found what might be possibly a bimodal metallicity distribution. And they said, or well, one interpretation is that the low metallicity corresponds to inflows and the high metallicity corresponds to outflows. We're going to look at this in more detail. Now, before that, I'll specify what we're talking about. Today, we're going to be talking about Lyman limit systems, or LLS. And we're going to find them as H1 absorption systems with, today defined, a column density between 10 to the 16.2 and 10 to the 19 per centimeter squared. There's other definitions, but that's the general region. More importantly, these are thought to trace CGM gas flows at low redshift. Our question then is framed as follows. Can the metallicity of LLS be used to distinguish inflowing from outflowing gas? And as I'll show you, the answer is yes, but that the traditional two-peak interpretation is not quite appropriate. So how are we going to be looking at this? We're going to be looking at this through the lens of the FIRE simulations. These are a series of cosmological hydrodynamic zoom-in simulations. They resolve the scale of the largest star-forming GMCs in their host galaxies. And they include explicit stellar feedback models for supernova, stellar winds, radiation pressure, photonionization, and photoelectric heating. Importantly, they reproduce a number of key observations, including the star formation histories, the ISM gas phase and stellar mass metallicity relation, and the high redshift LLS covering fraction. You'll be hearing a lot more about these throughout the workshop, I think, so stay tuned. Now, there's a few reasons why CGM gas flows are really workable for this. And one is that because of the galactic feedback, they self-consistently generate galactic winds. Also, because they are cosmological zoom-in simulations, they naturally include accretion flows. So for our particular analysis, we considered 14 zoom-in simulations with halo masses ranging between 10 to the 9 and 10 to the 13 solar masses. And we covered a redshift interval of 0 to 1 with 31 redshift slices. We're focusing today on cosmologically selected LLS, or LLS that are selected randomly without pre-selecting for galaxy halo. Our method overview is as follows. First, for a given simulation, we found the column density at multiple points, many different points, along the lines of sight. That's shown here. And then we selected the LLS. LLS and denser systems are outlined here in black. Once we have the LLS, we think about their metallicity and radial velocity. Here I show the metallicity in log of solar units, divided into a high metallicity red branch and a blue low metallicity branch in order to see the effects more clearly. Then we can take this and change it into a metallicity distribution function. And we do this for each redshift slice. Now, one thing to look at as you watch this movie is the high metallicity outflowing material, and also a significant amount of recycled gas as well that's equally metal rich. On the other side of things, there's lower mass, lower metallicity satellites, and other accreting material. This gives us hints that metallicity could be a good diagnostic, but that the picture is also relatively complex. Now, this is for a single simulation, and we did it for all 14 simulations, so we want to take that and turn them into a cosmological distribution. The idea to do that is as follows. We need to find the number of LLS contributing from a given simulation. So first, we want to find the likelihood of a quasar sightline intersecting a halo, which is proportional to the area of the halo times the halo mass function. Of that, you need to consider how many of those systems are actually LLS. That's quantified in the covering fraction. Convolve the two, and you get an important quantity, which is the number of LLS per unit redshift per unit halo mass. And you'll note that most of the LLS come from galaxies with a halo mass between 10 to the 10 and 10 to the 12 solar masses. The galaxies that are less massive than that have too few dense gas, just not enough. And the more massive galaxies have both a smaller covering fraction and are also fewer and far between. So now we have a general idea about the origin of the LLS. But is this correct? Well, we can compare to observations. Integrating our incidence of LLS per unit redshift per unit halo mass over halo mass, we can get the incidence of LLS per unit redshift, which we have some observations of. Here we're comparing to observations by Robato et al. From 2011, shown in the error bars for a few different column density cuts that still correspond to LLS. Our results are the curve. As you can see, there is a good agreement between our simulations and observations, allowing us to probe further and ask some questions that we really want to know, like, what does the metallicity tell us? So we look at the relationship between metallicity and radial velocity, and we look at the 2D probability distribution of the two. We find this for a given simulation, and then we combine it with all the other simulations weighted by the number of LLS per unit redshift per unit halo mass that are becoming from that individual simulation. And we do this over the redshift interval between 0 and 1 so as to reduce stochastic fluctuations. The result is shown here. The y-axis is the metallicity in log of solar units. The x-axis is the radial velocity in units of the host galaxy's circular velocity. The color axis is the density, so the probability density. So the darker the area, the more LLS. And you'll note that most LLS have a metallicity between -2 and 2. Or sorry, -2 and 0, and a radial velocity between -1 and 1. But importantly, the most strongly outflowing LLS, those with a radial velocity greater than 2 times the circular velocity, are consistently high metallicity. And conversely, the lowest metallicity LLS tend to have negative radial velocity. So what does this say about the two-branch interpretation? Well, if we then look at the cosmological metallicity distribution, so take that plot I had before and project it along the metallicity axis, you find this. This is the metallicity distribution. And as you might note, there's not strong evidence for two cleanly separated peaks. Further, if you look at the individual populations by inflows and outflows, defined by positive and negative radial velocity, you'll note that they're strongly overlapping. And the reason for this are somewhat straightforward. One, as we saw before, there are a wide range of contributing halo masses. And related to that, a wide range of outflow metallicities, which blur the lines. In addition, there's a significant amount of gas recycling and other dynamics going on that further blur the lines. This can draw us to our final conclusions, which are as follows. One, we were successful at matching the observed column density distribution. And we now know that from the simulations, most LLS come from galaxies with a solar mass with a halo mass between 10 to the 12 and 10 to the 10 solar masses. If we look at the interpretation of low metallicity being inflows, high metallicity being outflows, we see that it's not quite so simple because there's gas recycling and other dynamics going on, as well as a wide range of galaxy outflows with different metallicities. Nevertheless, metallicity is still a promising diagnostic, as the most strongly outflowing material is typically high metallicity, and the lowest metallicity systems have a typically negative radial velocity. In the future, we'll be extending this work by looking at the same ideas through a particle tracking analysis, where instead of dividing using instantaneous kinematics,